Good morning students, welcome to all. Today's session we see the crystal field splitting energy, one example. Okay, the previous video we saw the crystal field splitting energy example. Now I explain remaining one example, last example. Okay, first part I recall. In crystal field splitting energy topic, crystal field splitting energy depends on the nature of the ligand. Okay, children, crystal field splitting energy means, now this is the d orbitals, isotropic. Okay, no splitting. Here energy level is constant. So now splitting takes place. Okay, here totally 5 orientation. Okay, so this 5 orientation, this 5d orbital, now it involved in splitting, split. Okay, split in two ways. One is T2G. Okay, another one is EG. Okay, totally 5. 3 plus 2. This is one pattern. Another one pattern like this. 2, here 3. That's all. Are you clear, children? So now crystal field splitting energy. Okay, so here this another one. Okay, this one for tetrahedral, this one for octahedral. So in octahedral complex, again to filling the electrons in this orbital, its variation depending upon the nature of the ligand. Children, for example, d5 configuration. Okay, d orbital 5 electrons. This is the one way to fill the electron. 1, 2, 3. Okay, 4 and 5. This is one way. Okay, so in another one way to fill the electron like this. 2, 3, here 2. Okay, so this one for octahedral complex both. This one for tetrahedral complex. Okay, so now same orbitals, sorry, same electrons. Okay, d5 configuration. So 1, 2, 3, 4 and 5. This is the one way to fill the electron. This is another one way. Okay, so this one for high spin complexes. Based on this we fill the electron. That means here T2G 3, EG2. This one T2G 5 electrons. Okay, so this way we fill the electron mean this one high spin complexes. This one for low spin complexes. Okay, so this high spin as well as low spin is favored for strong field ligand or weak field ligand. Okay, children. So now in strong ligand, low spin is favored. This one keep in your mind. Okay, strong ligand, low spin complexes is favored. If the ligand is weak, high spin complexes is favored. Very clear, children? Okay, so up to this we saw in the previous video. Okay, so now I give one example. FeCN6 3 minus Cn, this one strong ligand. So now we apply the low spin as well as high spin. Next we come to the conclusion which one it is favored. Previous video we saw the example FeH2O 6 times. Okay, Fe, here also Fe, both also same metal, but ligand are different. Here water is the ligand, neutral ligand, okay, weak ligand. Here cyanide is a strong ligand. Cn minus negative type of ligand is an ambidextrous ligand. It is a strong ligand. Okay, this example previous video we discussed. Okay, this video we discuss FeCN6 3 minus. Then first find out the oxidation state of iron. Okay, so Fe consider as X, cyanide plus minus 1, 6 times, okay, equal to minus 3. So X minus 6 equal to minus 3. X equal to plus 6 minus 3 equal to plus 3. Okay, so what about the oxidation state of iron? Plus 3. Okay, so now write the iron atomic number, electronic configuration is everything. Okay, Fe 26, atomic number 26, electronic configuration 3d6 4s2. Okay, now in Fe plus 3 electron it is lost. So 2 plus 1, 3 electron it is lost. Remaining 3d5. Okay. So now Fe plus 3, outer electron 5 electrons. Okay. 3d orbitals. Now here apply the both high spin complex as well as low spin complex. Okay. Children, here now to apply the high spin as well as low spin complexes. Okay, so from that now to find out the crystal field stabilization energy for both high spin as well as low spin. Okay, now the crystal field stabilization energy value, if it is equal to 0. 0 means it denoted as it is a stable. Okay, so now the crystal field stabilization energy value, it is negative form. It is more stable. Okay. Children, this one note it in your textbook. Okay. Now maybe the answer is positive. It is unstable. So from that we come to the conclusion. Okay. Whether it is a high spin or low spin, it is favored. Are you clear, children? Okay. So now first find out the high spin complexes. Next one, low spin complex. High spin complexes. Children, find out the high spin complexes. Okay. Now D5. D orbital 5 electrons. Okay. 1, 2, 3, 4, 5 electron. This one isobaric center. Okay. Here no splitting. In the presence of ligand, it starts split. Okay, so now splitting takes place. Here 6 times it is a octahedral. So octahedral means T2G, lower energy level, EG, higher energy level. Okay, so here 5 electrons. Okay, in high spin complexes. High spin complexes 1, 2, 3, 4th electron and 5th electron. No pairing. Only in low spin it is pairing. Okay. Now T2G, how many electron? 3 electron. EG, how many electron? 2 electrons. Okay. Now to apply the crystal field stabilization energy, CFSE. Okay, you know the formula. What is the formula? N-T2G. Okay, into minus 0.4 plus EG. Okay, EG into 0.6. Okay, so whole term with delta 0 plus NP, pairing energy. Okay, so next minus NP prime P. This is the formula. You know very well. Crystal field stabilization energy. Okay, in T2G, number of electrons in T2G. Here how many? 3. Okay, so now apply here 3 into minus 0.4. Okay, next plus EG. How many electron? 2 electron. So 2 into 0.6. Okay, so overall it multiplied with delta 0. Are you clear? Okay, so next NP, pairing energy, minus NP dash. Okay, pairing energy. Here number of electron pair in ligand field. Here no pairing, so 0. This one for number of electron in here isobaric center, this position. So here all the electrons are single, so that also 0. Okay, so now here 3 4s are 12, a 0.4, so minus 1.2 plus 2 6 are 12, 1.2 minus 1.2 plus 1.2 cancel. Okay, so now 0 into delta 0, here 0, 0 into delta 0, 0. Okay, NP, P 0, NP prime P also 0. So here crystal field stabilization energy CFSE value equal to 0. So it is stable. Are you clear, children? Okay. So next we calculate the low spin complexes. Okay, low spin complex. In low spin complex, the electron filled in the orbital, it is a pairing pattern. Okay, so now 5 degenerate orbital, 1 2 3 4 and 5. So now splitting takes place. Okay, so here T2G, here EG, because it is a octahedral complex. Here 5 electron, so 1 2 3 4 and 5. Okay, here no electron, so T2G 5, EG 0. Okay, children, so now substitute in the formula. Okay, so T2G, how many electron? Now find out the crystal field stabilization energy equal to 5 into minus 0.4. Okay, plus EG 0. 0 into 0.6. 0. Okay, so the whole term is multiplied with delta 0. Okay, so next term. Plus NP pairing energy minus NP prime pairing energy. Okay, so this one denoted as this baric center, no pairing, all the electrons are single, so here 0. Here number of electrons in the ligand field, how many pairing? 1 set, 2, so 2. Okay, so now substitute the delta 0 as well as here pairing energy. So now 5 into minus 0.4. So minus 5 4s are 20. So 2.0. Okay. Here plus 0 into 0.6, 0. Okay. So here this one 0. So remaining delta 0. Okay. So plus NP, number of electron pair in ligand field, here 1 2, so 2 electron pair with pairing energy P minus NP, here no pairing. Okay, so 0. Now substitute the delta 0 crystal field splitting energy in octahedral complex is given in the textbook. Okay, 35,000, pairing energy 30,000. Okay, so now minus 2 into delta 0 35,000 plus 2 into pairing energy 30,000. Okay, so here minus 70,000 plus 60,000. So what about the remaining here? Minus plus, so minus 10,000. Are you clear? Okay. So now the CFSE value minus. Minus means denoted as more stable. Okay. So now FeCN63 minus is a more stable complexes. More stable compound. So which one it is favor? High spin or low spin? Here 0. Okay, stable. This one more stable. So low spin complexes is favored. Are you clear? Okay. So now in low spin complexes, find out the magnetic properties to calculate the number of unpaired electrons. Okay, so from that we find out whether it is paramagnetic or diamagnetic. Here number of unpaired electron, it is 1. So it is paramagnetic in nature. Okay, paramagnetic in nature. Okay, number of unpaired electron, n value equal to 1. So mu s, spin only magnetic moment, equal to root of n into n plus 2. Okay, n value 1. So substitute in the formula 1 into 1 plus 2 square root. So answer 1 means 1.7 Bm, Bohr magneton. Are you clear, children? So from the crystal field stabilization energy are using the CFSE now to find out the coordination compound is whether it is paramagnetic or diamagnetic. And next, from the low spin as well as high spin, we come to the conclusion the ligand is weak field ligand or strong field ligand. Okay, so next to calculate the mu s. Okay. Next topic, color of the complex. Children, maximum transition elements, transition compounds are colored substance. You know very well. Okay. Especially transition elements, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. In coordination complex, the substance is colored. Okay. So now it is explained in the textbook, give the wheel diagram. Okay. Now I am drawing like this. Okay, it's very helpful for you. Now violet, indigo, opposite side yellow. So the substance absorb the particular wavelength. Okay, so now it emit the light as the complementary colored. Okay, so the substance absorb violet color. Now it come out or it transmit in the yellow color. Okay, so same way for red, green, blue, orange. Okay, so now 4000 Armstrong. Okay, it absorbs at a particular wavelength. Okay, so it expressed in Armstrong as well as nanometer. So Armstrong 10 power minus 10 meter. Nanometer means 10 power minus 9 meter. You know very well. Okay, so now I am here writing one example and explain how it is the substance, it is a colored complex. Okay, so the main reason is here involved the DD transition. Okay, so D transition, D and D. Due to D transition, the substance are colored. Are you clear, children? Okay, so now writing the example, titanium H2O 6 times 3 plus. Okay, so first to find out the oxidation state of titanium. So X, water molecule, neutral ligand, so 0. So X is equal to 3 plus. So what about the oxidation state? 3 plus. What is the titanium atomic number? The second element, scandium, titanium. Okay, so 3D2, 4S2. Here titanium plus 3. So 2 plus 1, 2 electron from 4s and 1 electron from 3D orbital, it is lost. So what about remaining titanium 3 plus 3D 1 configuration? Okay, here water molecule 6, it is a octahedral. Okay, so now D orbital 1, 2, 3, 4, 5. Here only 1 electron. Okay, so now it involved in the crystal field splitting takes place. So now it is a octahedral. So T2G right at the lower energy level and Eg right at the higher energy level. Okay, so now only one electrons. Now to pass the white light, okay, at a particular wavelength, so it absorbs the at a particular wavelength, and this electron now it move to the higher energy level Eg. Okay, here no electron, so this also d orbital, this also d, so d transition, it move from lower energy level to higher energy level. Okay, so now again it come back, mean it emit the radiation, it emit the complementary color, it come out, so it complementary color is purple color. Are you clear, children? Okay, so now here d transition it involved. Now from the D to G, one electron it moved to the Eg level, excitation. This one for ground state, this one for excited state. So now electron move from here to here. So d transition. Can you understand the word, children? d transition takes place. So now the color will appear, or color it produced. Especially it produced the complementary color. Okay, but here now to pass the white light, but it comes out as in the purple color. Okay, the same way for in BB theory or Werner theory, whatever, they never explain the colored compound. Okay, so only the crystal field topic it is possible to explain the transition complex or the colored substance due to d transition. Okay, but why here VB theory it is not explained, mean here no splitting energy, only the electron present in, for example here 5, okay, 5d orbitals, electron it is present here, maybe now this electron it move to the next level, mean it move here, here, so no energy difference. Okay, here the splitting energy is present, so now electron move from ground to excited state. Okay, so during this that is a movement from here to here, again it come to the original. Okay, so now it emit the radiation formation, you know very well concept. So due to this reason, now the transition complex or the colored substance. Titanium H2O6. Now you know the complex is purple color. Okay, but at the same time I writing the example titanium F6, titanium Br6. But here everything is the same metal, but ligand are different. But here we never expect as the purple color the complexes, because the splitting energy is variation. Okay, so even now studied high spin and low spin complexes, which one it is favored depending upon the nature of the ligand. So here the splitting energy is variation. Okay, so now different color will produced. Okay, but the metals are same. Are you clear, children? Okay, so at the same time in the transition element, some elements are exception case. Okay, so in scandium 3 plus oxidation state, as well as titanium 4 plus oxidation state, now d orbital is 0. I want writing the example clearly. Scandium atomic number 21, electronic configuration 3d1 4s2, Sc plus 3 electron it is last, so 2 plus 1 3 electron it is last, so 3d0. Okay, children, so now d orbitals no electron, so no transition. We never expect the transition in 3d orbital because here are no electron, children. So no dd transition takes place. Only due to the dd transition the complex is colored. Here no d orbital, no electrons in d orbital, so no dd transition, so it is colorless. Okay, at the same time, see the another type of example, Cu plus and Zn2 plus. Okay, For example, here zinc atomic number 30. Okay, Zn atomic number 30. So 3d10 4s2 electronic configuration. Now Zn plus 2. So 2 electron it is lost. What about remaining 3d10? So d10 configuration. Same in Cu plus also. So in d orbital it is completely filled. So here no transition takes place. Are you clear, children? So here also Cu plus as well as Zn2 plus, it is a colorless compound because no DD transition. Next topic, metallic carbonyl. Metal. Now it studied the transition metals. Okay, the coordination complex is combined with only the transition metal. So transition metal with carbonyl group. See one example: transition metal nickel, carbonyl CO. Okay, so here 4 times. Now metal nickel, it link with carbon and oxygen. So metal as well as C now arises the bond. So bond between nickel as well as carbon. Here oxygen. Okay. So this one homolyptic complexes. So homolyptic means same type of the ligand it is present. So same type of ligand mean here CO. CO is the neutral type of ligand, you know very well. Okay, what are neutral ligand? This one for this also CO is the neutral ligand. So this one studied elaborately. Okay, so is uses is many ways it is useful for that. For example, in the industrial purpose, as well as this complexes used as a catalyst. Okay, at the same time here it is ability to remove the CO group. Okay, so this is the importance of the metallic carbonyls. Okay, here studied the classification of metallic carbonyls. Okay, it classified into it is based on this classification. It is based on 2 ways. One is based on the structure. Okay, based on number of metal. Okay, so classification of metal carbonyl, it is based on 2 ways. One is based on the structure and another one is based on number of metal atom present. Okay, so first one, this based on number of metal atom, it again it classified into 2. Okay, mono denoted as only one. Okay, mononuclear carbonyl, and another one is polynuclear carbonyl. Okay, so here mono means it contain only one metals. See this example, Fe, first NiCO4, nickel tetracarbonyl. Okay, FeCO5. Next, CFCO6. Here, how many metal it is present? But ligand is variation 4, 5, 6. But metal only one metal. Okay, so in mononuclear carbonyl, it contains only one metal. So next one, this one polynuclear carbonyls. So in polynuclear carbonyls, nuclear carbonyl, it again classified into 2. Okay, one is homonuclear carbonyl and another one is heteronuclear carbonyl. You know, homo means same, hetero means different. So same type of metal, but at the same time here poly means more than one or 2 or more. Okay, so now homonuclear carbonyl example, CO2 CO8 times. or whatever, okay, chromium, whatever, any metal. Now here cobalt 2 times homonuclear. At the same time, heteronuclear carbonyl means CO, Mn, CO, 9. Very clear? This one for cobalt, Mn. This one CO, carbonyl. But here all the example, it contain the carbonate, same type of ligand. Okay, so homolyptic ligand. Okay, so now here same type of metal it is present. So homonuclear carbonyl example. Next example here, different metal. So it comes under the heteronuclear carbonyl. Children, now study the classification of metallic carbonyl. Transition metal with CO. Okay. So we know the application also. So study the classification. Next bonding, stability, everything we studied here. So first one, classification. It is explained based on number of metal atom present in it, and another one based on structure. Okay, so based on structure mean it is based on the non-bridged as well as bridge. Okay, explained. So now we see the number of metal atom present in it. So it is classified into, one is mononuclear carbonyl, mononuclear carbonyl, and another one is polynuclear carbonyl. Mononuclear carbonyl mean the carbonyl compound or metallic carbonyl contain only one metal. Okay, so polynuclear carbonyl compound mean it contain two or more metals. Okay, again it is classified into two. One is homonuclear carbonyl and another one is heteronuclear carbonyl. Homo, it is denoted as same type of metal it is present. Hetero denoted as different. So different type of metal it is present. So here this one example for homo as well as hetero. Based on structure, classification of metallic carbonyl, it is two classification. One is non-bridged metal carbonyl and another one is bridged metal carbonyl. First we see the non-bridged metal carbonyl. Children, from the word itself we come to the conclusion. No bridge between the metal. Okay. Here one new word, terminal carbonyls. In terminal carbonyls shows the carbonyl group is attached to the one metal atom. Okay, so see this example, NiCO 4 times nickel, only one metal. Okay, so now 4, so it is a tetrahedral shape. Okay, so CO, CO and CO, CO. Here I have no bridge. So non-bridged metal carbonyl. Okay, so next example, FeCO5, FeCO5. So here 5 ligand, so trigonal bipyramidal, CO, 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 CO and CO, center Fe, trigonal bipyramidal. Okay, so next Cr, CO6. Here center Cr, this one for octahedral, CO, 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 here also CO, here also CO. Okay, so totally how many? 6. Okay, so it is an octahedral complex. Here have no bridges, non-bridged metal carbonyls. Okay, so here this one for terminal carbonyl group present at the terminal position. Okay, that denoted as CO group is attached to the metal, one metal, that denoted as terminal carbonyl group. Okay, so here in non-bridged metal carbonyl, this one for terminal carbonyl, as well as here metal bond also it is possible. See this example, Mn2, okay, CO10, 2 CO10, okay, Mn, transition metal, Mn, here CO 10 times, so here 5, here also 5, so 1, 2, 3, 4 and 5. Put the arrow mark. This arrow mark denoted carbonyl group, donate a pair of ligand. Okay, so same way for here. So 5 CO group, CO carbonyl. Here metal bond. Okay, so now this in, but at the same time here no bridge between metal. No bridge takes place. Okay, so non-bridged metal carbonyl, it explains two ways. One is only the terminal carbonyl, and second one terminal carbonyl as well as metal bond takes place. So next one we see the bridged metal carbonyl. This example, Fe2CO9. Here Fe and Fe. So first write the terminal carbonyl. 1, 2, 3. 1, 2, 3. CO and CO and CO. Okay. So C right here. CO and CO. So totally 6 CO group, remaining 3. Okay. So CO. Now bridge takes place between metal as well as metal through the CO. Same way for here, CO and CO. And remaining one more CO we have. So CO and CO. Are you clear, children? So this is the bridged metal carbonyl. Now this one for terminal carbonyl. This one denoted as bridged metal carbonyl. Okay, so here also give this example and how many isomer is possible we expect. Okay, so see the next. CO2, CO 8 times. Okay, so here CO, cobalt. This one carbonyl group, 1, 2, 3, 4. Okay, here metal bond, 1, 2, 3 and 4. So CO and CO and CO. This is the one example. Okay. Here only the terminal carbonyls. Here bridge between metal as well as metal. So next cobalt and cobalt. Okay. So here 8. 1, 2, 3, 4, 5, 6, 7. This one for 8. So now here metal, another one bridges. So next one terminal carbonyl also it is possible. Next topic, stability of metal complex. Stable. So normally see here the, for example, nitrogen and oxygen, we compare to which one is more stable. Okay, nitrogen is more stable. How? Nitrogen outer electronic configuration is half filled. Okay, whether it is a half filled or completely filled, it is more stable. Okay, so at the same time inert gas elements also it is a more stable. It does not react with any other. Now we studied in coordination complex. The compound is talk about the stability of the complex. Okay, so the stability of the complex it explained in two ways. One is thermodynamic and another one is kinetic stability. Thermodynamic. Okay, thermodynamic stability and another one is kinetic stability. So in thermodynamic stability it refers to the free energy changes. Free energy changes symbol delta G. Now delta G is negative, it is a spontaneous reaction. We know very well. Okay, so next one, kinetic stability. So this kinetic stability explained or referred based on their ligand substitution. Okay, so now the substitution of ligand is fast process, very rapid, mean the complex is called as, okay, so here ligand, it is based on ligand substitutions. Okay, so now this ligand substitution, if it is fast and slow. Okay, so now fast mean it is called as labile complex. Okay, and very slow, it denote the complex is inert complex. Okay, children. So now see one example. You can identify very clearly. Metal, ligand, 6 times. Now substitute the ligand, another one ligand, for example X. So now it is in labile complex, means now substitution takes place, fast reaction. So what about the product L5? One ligand is removed. Now the next part of ligand is substituted, X plus L. But in inert complexes, see this example, Ml6, metal ligand, 6 ligand 6 times octahedral complex, react with another one type of ligand. Now to use, what about the product? This one slow process, this one inert complexes. So inert means no reaction takes place. So we get the product is Ml6 plus X. So this one for inert complexes. Children, now study the topic stability. So it is based on 2 ways. One is thermodynamic and another one is kinetic. In thermodynamic, it is explained based on the delta G concept, and the kinetic stability, it is explained based on the ligand substitution. Ligand substitution fast. The complex is known as labile complexes. If it is slow, means inert complexes. And in labile complexes, we get the product like this. In inert complex, is the products is again repeated. Okay, the reactant we get back again. Okay, no reaction takes place here. Children, I hope you understand this session. Okay, thank you, children.